A Bill Gates-backed nuclear fusion company has teamed up with some of the most powerful names in modern technology to bring the energy of the sun a step closer to commercial reality. Commonwealth Fusion Systems, the largest and most well-funded private fusion company in the world, has announced a deep collaboration with NVIDIA and Siemens to build a digital twin of its Spark fusion reactor. This partnership brings together three different worlds: cutting-edge artificial intelligence, industrial-scale engineering software, and one of the most ambitious energy technologies ever pursued, into a single coordinated effort. This is not a marketing demo, nor a speculative visualization. It is a working, physics-accurate virtual replica of one of the most advanced fusion machines humanity has ever attempted to build. The goal is to compress years of physical trial and error into weeks of AI-driven simulation, optimization, and interaction. Instead of learning slowly through expensive hardware changes and limited experimental runs, engineers can now explore thousands of operating scenarios with AI, identify failure points early, and redefine designs before committing changes to the real machine. In traditional fusion development, every experiment is slow, costly, and constrained by the limits of physical hardware. NVIDIA-powered AI changes that equation entirely. It allows fusion engineers to explore what-if questions at a scale and speed that was simply impossible before. And NVIDIA is not the only company investing in fusion. OpenAI, Google, Microsoft all have billion-dollar partnerships in fusion tech. But before going further, it's important to clarify what fusion actually is, because it's not the same thing as nuclear power plants operating today. Current nuclear plants use fission, which means splitting heavy atoms like uranium apart. That process releases large amounts of energy, but it also creates long-lived radioactive waste and carries meltdown risks if cooling systems fail. Fission reactors require complex safety systems and long-term waste management strategies, which has made public acceptance and large-scale expansion politically difficult in many parts of the world. Fusion does the opposite. Fusion joins light atoms, typically isotopes of hydrogen, together. When they fuse, a small amount of mass is converted directly into energy, following Einstein's equation, E=mc². This is the same fundamental reaction that powers the sun and all the stars across the universe. Instead of breaking matter apart, fusion builds it together, releasing enormous energy in the process. The advantages are profound. Fusion fuel is abundant and widely available, often derived from hydrogen isotopes found in water. Fusion reactions do not produce carbon emissions. They cannot run out of control in the same way fission can, because sustaining fusion requires extremely precise conditions. If those conditions are disrupted, the reaction simply stops. And fusion does not generate long-lived radioactive waste that remains hazardous for thousands of years. The promise of fusion has never been in doubt. The problem has always been engineering. To make fusion work on Earth, you must heat plasma, an electrically charged gas, to temperatures hotter than the center of the sun. Then you must confine the plasma long enough and stably enough for the reaction to produce more energy than it consumes. That challenge defeated generations of scientists. This is where the collaboration between CFS, NVIDIA, and Siemens becomes transformative. CFS will use NVIDIA Omniverse libraries and OpenUSD to integrate detailed engineering data with both classical physics models and AI-powered simulation systems to create a living digital twin of Spark. This virtual replica allows engineers to run simulations, test hypotheses, and directly compare experimental results from the real reactor against predicted outcomes inside the model. Instead of operating in isolation, the physical machine and the virtual machine evolve together. Data from experiments feeds back into the model. The model improves. New simulations guide the next set of experiments. This creates a continuous feedback loop between reality and simulation. This ability to rapidly analyze data and iterate is expected to significantly accelerate CFS's effort to turn fusion energy into a commercial reality. What once required long experimental cycles can now be explored virtually, dramatically reducing risk and uncertainty. CFS is also using Siemens digital tools to improve efficiency at the manufacturing level, particularly at its magnet factory in Devens, Massachusetts. These magnets are among the most critical components of the entire fusion system. A single fully energized magnet could theoretically lift an aircraft carrier. Every detail from material properties to assembly tolerances is digitally tracked and optimized before the physical components are produced. CFS is not alone in recognizing this shift. Across the fusion industry, nearly every serious player, OpenAI, Google, Grok, is now tightly connected to the fusion power through investments, partnerships, or direct power purchase agreements. Sam Altman's $5.4 billion nuclear fusion startup Helion Energy is pursuing a radically different fusion approach. Instead of relying on tokamaks and turbines, Helion collides rings of plasma at extreme speeds. The fusion reaction perturbs magnetic fields, which are then used to generate electricity directly through electromagnetic induction. This design eliminates the need for boiling water or spinning turbines, which immediately simplifies the overall system. Traditional power plants, whether coal, gas, fission, or even many fusion concepts, rely on heat to produce steam, which then spins massive turbines to generate electricity. That entire chain adds mechanical complexity, efficiency losses, maintenance challenges, and cost. Helion's approach bypasses that altogether. By converting the energy of fusion directly into electricity through electromagnetic induction, the system becomes more compact, more efficient, and potentially far easier to scale. Helion has already signed a contract to deliver fusion power to Microsoft, a deal that has become one of the most closely watched agreements in the entire energy sector. What makes it unusual is not just the ambition, but the accountability built into it. The contract reportedly includes financial penalties if Helion fails to deliver on its timeline, something almost unheard of in fusion history. That detail alone signals how seriously both sides are treating the possibility of near-term fusion power. The company also claims that its current system already recaptures most of the energy it puts in, placing it close to engineering break-even. That does not mean the problem is solved, but it does suggest Helion is operating much closer to the finish line than fusion companies of the past. If those claims hold up under continued testing, it would represent a meaningful shift in how quickly fusion could move from experimental to commercial. Sam Altman has been explicit about why he is investing so heavily in fusion. He has repeatedly argued that the future of artificial intelligence depends on energy breakthrough, and that incremental improvements to today's power systems will not be enough. As AI systems scale, their energy demands do not increase linearly, they compound. Fusion, in Altman's view, is the only option that scales cleanly without undermining climate goals, grid stability, or geopolitical energy constraints. But Helion is only one path forward. Across the fusion landscape, other companies are exploring fundamentally different approaches, each betting that a unique solution to plasma control will unlock commercial power first. TAE Technologies, also backed by Google, is pursuing a beam-driven field-reverse configuration. Instead of confining plasma into a donut-shaped tokamak, TAE's approach stabilizes plasma, using particle beams that actively shape and control the reaction. The goal is to achieve stability through motion and feedback rather than brute force magnetic confinement. It's a more dynamic approach, and while technically demanding, it offers potential advantages in efficiency and long-term operation. Pacific Fusion is revisiting inertial confinement fusion, the same broad category used in national laboratory experiments, but with a commercial mindset. OpenStar, based in New Zealand, takes yet another route. They achieved first plasma based on the levitated dipole approach. It inverts the traditional magnetic bottle concept entirely, placing an ultra-strong magnet at the very center of the reactor. Plasma is then confined around this central core, rather than inside an external magnetic ring. This geometry aims to reduce system complexity and improve stability by rethinking where confinement begins. It's a radical design, but one that reflects how open the fusion problem still is to new ideas, different physics, different geometries, different engineering philosophies, but the same ultimate goal, and who wins rule the next AI race. If you look at China today, you can already see what happens when a country tries to brute force AI growth with existing energy technologies. China is not waiting for fusion, it is scaling everything else at once. Massive solar bases like the Tengger Desert Solar Park and the Gonghe Solar Park now span tens of square kilometers, producing gigawatts of power in remote regions. Hydropower projects operated by China Three Gorges Corporation, including the world's largest dam, provide stable baseload electricity, while conventional nuclear power plants, built by China National Nuclear Corporation, are being added at a pace unmatched anywhere else. To move this energy to AI hubs, China has constructed an enormous network of ultra-high voltage transmission lines operated by State Grid Corporation of China, capable of sending power thousands of kilometers from western solar and hydro regions to eastern data center clusters. This strategy works, but it's complex, land-intensive, and tightly coupled to geography, weather, and grid stability. But USA doesn't have the privilege. That's why fusion is the only hope for future energy. If fusion succeeds at scale, the implications for artificial intelligence are enormous, especially when compared to how today's AI powers are trying to solve the energy problem. A single commercial fusion plant could realistically produce hundreds of megawatts to multiple gigawatts of continuous electricity, enough to power entire hyperscale data center campuses on its own. That would free companies like Google, Microsoft, OpenAI, and Meta from grid constraints, peak pricing, and regional power shortages. So the path toward AGI. Intelligence at that level is not just a software problem, it's an infrastructure problem. Thanks for watching. If you want the real story behind the world's fastest moving and AI tech breakthroughs, make sure to like and subscribe to Evolving AI for daily coverage.